Start with an overview of the electrical system. The electrical system consists of the AC system, the DC system, and standby system. AC electrical power can be supplied from one of four sources: either engine generator, the APU generator, or a ground power source. Transformer rectifiers, commonly known as TRs, convert AC power into DC power. The TRs are the primary source of DC power for the DC system. The aircraft battery provides an alternate source of DC power. Let's look at the AC system. The two engine-driven generators are the normal sources of power for the AC system. The number 1 engine-driven generator supplies generator bus number 1, and the number 2 engine-driven generator supplies generator bus number 2. The two generator buses then distribute power to the airplane. The engine-driven generators rotate at a constant speed by means of a constant speed-driven mechanism, or CSD. The CSD maintains a constant shaft rotation speed at all engine speeds. The CSD has a self-contained oil system and generator drive disconnect mechanism. Each engine-driven generator supplies three-phase 115-volt AC electrical power at frequency of 400 Hz. A generator control unit, or GCU, monitors the output of the engine-driven generator. The GCU will allow the generator to connect to the electrical system only if the generator output, both voltage and frequency, are within limits. There are no provisions for paralleling electrical power source. Therefore, only one power source can be connected to a power bus at any given time. In this example, the engine-driven generators are powering their respective buses. Two other AC electrical sources can power the aircraft's electrical system: the APU and an external electrical ground power cart. The APU can also supply power to either generator bus. On the ground, the APU can power both generator buses at the same time. In flight, the APU can only power one generator bus up to a certain altitude. The APU generator is similar to the engine-driven generator, except that there is no CSD mechanism. The APU turbine speed is controlled to maintain a constant APU generator output. The APU also produces three-phase 115 volts AC electrical power at frequency of 400 Hz. The power output is also monitored by a GCU. An external electrical ground power cart can supply power to both generator buses. The generator buses can be powered simultaneously from any combination of AC power sources. In this example, the ground cart is supplying AC power to generator bus number 1, while generator bus number 2 is being powered by the APU. Now, let's examine the power distribution from the generator buses. Generator bus number 1 powers main bus number 1 and transfer bus number 1. Generator bus number 2 powers main bus number 2 and transfer bus number 2. A bus transfer system ensures that a transfer bus remains powered in the event the associated generator bus fails. When a generator bus is not powered, its transfer bus automatically connects to the powered generator bus. After the transfer has taken place, most of the electrical system remains powered, with the exception of the failed generator bus and its associated main bus. Let's look at the DC electrical system now. The DC system is normally powered by a series of transformer rectifiers, or TRs. A TR converts 115-volt AC current into 28-volt DC current. There are three transformer rectifier units: TR1, TR2, and TR3. The transfer buses power TR1 and TR2, while TR3 is powered by main bus number 2. TR1 powers DC bus number 1. TR2 powers DC bus number 2. TR3 is the primary source of power for the battery bus. It is also used as a backup power source for DC bus number 1 and 2. The DC circuit design is such that TRs 1 and 2 also provide backup power to each other. A DC disconnect relay isolates TR1 from TR2 and 3 when at glide slope capture during a flight director or autopilot ILS approach, or when the bus transfer switch is placed to off. The purpose of this relay is to provide independent electrical power sources for the captain's and first officer's navigation receivers and auto-flight system. This is a requirement for Cat 2 and Cat 3A certification. A 24-volt battery supplies DC power to start the APU and to power essential equipment when the aircraft has lost all electrical power. A fully charged battery can power the essential equipment for 30 minutes. A battery charger maintains the battery charge by converting 115 volts AC into 28 volts DC. The battery charger is normally powered by the ground service bus. If the ground service bus is not powered, the battery charger is powered from main bus number 2. Therefore, the battery charger is powered if either generator bus is powered. The battery bus supplies the hot battery bus, the switched hot battery bus, the battery bus, and the standby system. The standby system will be discussed later on in this module. The ground service bus supplies electrical power to utility outlets located throughout the cabin, the battery charger, and it is used for cabin lighting. When the ground service bus is powered, ground personnel can clean the aircraft while the other electrical buses are unpowered. Let's look at the standby system. The AC and DC standby buses are powered from transfer bus number 1 and DC bus number 1 respectively. The standby buses supply power to some of the essential flight instruments and radio equipment in the airplane. The backup power source for the standby AC and DC is the battery bus. The AC standby bus receives power from the battery bus through the static converter. The DC standby bus is powered directly from the battery bus. Notice that the battery can also supply power to both the AC and DC standby buses. A fully charged battery can provide a minimum 30 minutes of standby power. Let's look at the controls and indicators for the electrical system. The control and indicator panels for the electrical system are located on the forward overhead panel. They include the AC and DC meters and the GALLEY power control panel, the generator drive control panel, the ground power control panel, and the bus switching panel. Let's look at the generator drive control panel. The generator drive disconnect switch is used to disconnect the CSD. The red guard prevents an unintentional generator disconnect. As long as battery bus power is available, positioning the switch to disconnect disconnects the generator from the engine, trips the generator off the bus, and disconnects the generator field. Once disconnected with the switch, a generator cannot be reconnected while in flight. A reset can only be accomplished on the ground. Oil is used to cool the CSD. As the oil flows out through an oil cooler, fan air is used to cool the oil before it flows back in. Temperature sensors measure the CSD oil temperature. This temperature is displayed on the associated CSD oil temperature indicator. Two different types of CSD temperatures can be monitored. The temperature to be displayed is selected by the generator drive temp switch. It has two positions, in and rise. When the temperature selector switch is positioned to in, the temperature of the oil entering the generator is displayed on the indicator. The temperature is read on the inner scale of the temperature indicator. The scale ranges from 40 to 160 degrees centigrade. When the generator drive temperature switch is positioned to rise, the outer scale of the temperature indicator displays the difference between the temperature of the oil leaving the CSD and the temperature of the oil as it enters the CSD. The displayed value is an indication of the generator drive workload. An oil pressure sensor monitors CSD oil pressure. The low pressure light on the drive generator panel illuminates if the oil pressure is below minimum operating limits. The electrical annunciator and both master caution lights illuminate. The high generator oil temperature light illuminates if the temperature of the oil entering the CSD exceeds operating limits. The electrical annunciator and both master caution lights will illuminate. We will now look at the function of the standby power switch. The normal power sources for the standby buses are transfer bus number 1 and DC bus number 1. The backup source of power is the battery bus. The battery bus supplies DC power directly to the DC standby bus. An inverter converts DC power from the battery bus into 115-volt single-phase power to the AC standby bus. The standby power is controlled by the standby power switch. The switch has three positions: battery, off, and auto. The switch is guarded to the auto position. The auto position arms the auto transfer feature of the system. This feature is available while in flight only. The AC and DC standby buses will be powered from the battery bus in the event of the loss of DC bus 1 or transfer bus 1. Remember that TR3 is the primary source for the battery bus and that the battery is an alternate source. On the ground, this automatic transfer feature is deactivated and the standby buses will not be powered. With the standby power switch off, the standby buses are not powered. Whenever the AC standby bus is not powered, the standby power off light illuminates. The battery position connects both standby buses to the battery bus regardless of any available power sources or whether the airplane is in flight or on the ground. The battery position of the standby power switch also forces the battery bus to be powered from the airplane battery. We will now look at the bus switching panel. The generator switches are used to connect the associated generator to its respective bus. The switch is spring-loaded to the center or neutral position. Momentarily positioning the generator switch to on closes the generator field and the generator breaker if sufficient power is available. If the associated generator bus is powered by another source, this source is removed. The AC ammeter now indicates that there is a load on the generator. The associated bus off light is extinguished, indicating that the generator bus is powered. Positioning the generator switch to off opens the associated generator field. This, in turn, causes the generator breaker to open. The generator off bus light illuminates when the associated generator breaker is open. We will now discuss the APU generator. The APU drives a single generator which can be used as an alternate power source for the generator buses. APU generator output can be connected to either the number 1 or number 2 generator buses by means of the two APU generator switches. A blue APU generator off-bus light illuminates when the APU generator is up to speed but is not connected to either generator bus. Placing either generator switch to on connects the APU generator to the respective generator bus and extinguishes the APU generator off bus light. The previous power source is disconnected when the APU powers either generator. The APU generator uses a generator control unit to verify that the APU generator output is within limits. The next item of interest on the generator control panel is the bus transfer switch. The bus transfer switch controls the operation of the bus transfer system. It is a two-position switch guarded to the auto position. If a transfer bus is not powered, the associated transfer bus off light illuminates. The electric annunciator light and the master caution lights illuminate. With the bus transfer switch in the auto position, a bus transfer relay automatically connects an unpowered transfer bus to an operating generator bus. The powered generator bus now supplies both transfer buses. The auto position of the bus transfer switch also allows main bus number 2 to provide backup power to the battery charger in the event that the ground service bus is not powered. With the bus transfer switch in the off position, the automatic bus transfer system is deactivated. Therefore, the operating generator will not be able to power the unpowered transfer bus. The off position of the bus transfer switch isolates the main buses and removes the backup power source for the battery charger. The off position of the bus transfer switch will open the DC disconnect relay. This affects the backup capabilities of the TRs. Recall that TR1 and TR2 are able to provide alternate sources of power for each other, and that TR3 can back up TR1 or TR2. The auto position of the bus transfer switch closes the DC disconnect relay and allows the TR to provide this backup capability. With the switch in the off position, the TR3 disconnect relay is open, thereby isolating DC bus 1 from DC bus 2. The generator buses can also be powered by an external electrical power card, or GPU. The ground power switch is a 3-position switch, on, off, and spring-loaded to the center neutral position. It controls the ground power relays and enables an external electrical power card to power the generator buses. Illumination of the ground power available light indicates that a GPU is plugged into the external AC receptacle. Note that the ground power available light does not indicate the ground power unit power is within limits. Placing the ground power switch to on connects external power to both generator buses. GPU output is checked by a bus protection panel. This action also removes any previously connected power sources from both generator buses. If the APU is available and connected to the generator bus, the opposite generator bus will remain powered by the ground cart. This permits a no-break power arrangement for the electrical buses when transferring from external power to the APU generator. Power transfer from the external ground power cart to either engine may be accomplished in the same manner, without an interruption of power to the electrical buses. We will now look at the battery switch. The battery switch controls DC power to the switched hot battery bus and the battery bus. The battery switch is a two-position switch guarded to on. When the switch is on, the primary power source of the battery bus is TR3, and the alternate power source is the hot battery bus. When the battery switch is off, both the battery bus and the switched hot battery bus are not powered. However, if the battery switch is off and the standby power switch is placed to battery, the battery bus will receive power directly from the battery through the hot battery bus. Now, let's look at the DC metering panel. DC loads are displayed on the voltage and amperage meters. The DC meter selector selects the power source to be monitored. The standby power and battery bus positions display voltage indications only. The battery position displays the voltage and amperage loads of the 24-volt battery. When the battery charger is operating, the meter indicates 28 to 30 volts with positive amperage. When the battery is fully charged, the voltage will remain at 28 and the amperage indication will be near zero. Each transformer rectifier can be monitored individually. The normal output of a TR is 24 to 30 volts. The amperage will vary with the demand and will read with a slight positive reading to the TR limit of 65 amps. A zero amperage reading implies a malfunctioning TR, even though its voltage appears to be normal. TRs never display a negative reading. The test position is used by maintenance. Now, let's look at the AC system indications. These meters are used to monitor frequency and voltage. The power source to be monitored is selected by the AC meter selector below the meters. Engine and APU generator output are identical. These generators and the ground power cart normally produce 115 volts AC at a frequency of 400 Hz. Selecting standby power displays the frequency and voltage of the AC standby bus. Normal frequency and voltage are 115 volts and 400 Hz, regardless of the power source to the bus. The static inverter position checks inverter voltage output similar to the standby power position. The test position is used by maintenance. The voltmeter has two scales. The outer scale is used during normal operation. The inner scale indicates the residual voltage of the selected generator. If the selected generator drive is disconnected, the residual voltage is near zero. To prevent damage to the meter, do not press the residual volts button if the generator breaker and generator field relays are closed. Let's look at how the galleys are powered. The galley power switch controls power to the forward and aft galleys. Galley area lighting is not affected. The electrical system incorporates an auto galley load shedding. During single generator operations, all galley power is shed regardless of the position of the galley power switch. This reduces the load on the operating generator to prevent an overload. The Boeing 737-500 model incorporates an additional overload protection circuit. This circuit is armed when the APU is powering the main buses. When an overload is sensed, the galley power switch automatically trips to the off position, shedding galley power. Galley power can be restored by placing the galley power switch to the on position after the overload condition has been rectified.